I would like to thank the organizers for organizing Strings 2014 in this wonderful place. I would like to also thank them for inviting me to give a talk here. Coming back to Princeton is always wonderful. It brings great memories for me as when I was a graduate student here. I'm going to talk about some work we have done on 6-dimensional superconformal field theories. This is based on works with a number of collaborators, Jonathan Heckman, David Morrison, and also work to appear with Del Zetto and Heckman and Tomasiello. These two works are related to classification of 6D superconformal field theories. And also some work related to computations involving these theories, which are with Babak Haqiqat and John Kostchas, Guglielmo Lockhart, my student, as well as some work to appear, which recently appeared. So 6-dimensional superconformal field theories enjoy a unique status. They are the highest dimension known non-trivial conformal field theories. And we have two types of them, depending on the number of supersymmetries. The 2, 0 believed to be classified by an ADE classification, where the A-type classification corresponds in the M-theory language to having a stack of parallel M5 brane, which are coincident. And the D and the E version are better described in the type 2B setup, where we have a type 2B with an ADE singularity. Then there's a 1, 0 version of the superconformal theories with half the supersymmetry. And these are more difficult to classify. There has been many interesting examples over years. And we have a number of examples that we can play with. These correspond to having the analog of n equal to 2 supersymmetry in 4 dimension, or 8 supercharges, half as many as these guys. There are two aspects to studying these 6-dimensional superconformal theories. One is to classify them. So the main emphasis here, the main topic of my discussion is going to be the 1, 0, because 2, 0 is already classified, presumably. And so we want to talk about how to go about classifying the 1, 0 theories. And we will use the type 2B or FDA realization for this. And then the second part, which is going to be somewhat shorter, is the development of tools to study each of these conformal theories. And in this context, we focus on the properties of the tension of the strings and the theory that the word sheet of these strings C, which in the M-theory language would correspond to suspended M2 branes. And this part I will be more brief on because I've already discussed this in the last strings. And I will just present some of the updates which has happened since the 2013 talk I gave. Now, in these theories, there are two types of deformations one can study in the context of conformal theory. One is to go to the Coulomb or tensor branch. This corresponds to having we will end up having a bunch of tensor multiplets which have a scalar and a tensor field. And these scalars are used to quantify the tension of the corresponding strings, which couple to the B mu nu. And then there's the Higgs branch, which is captured by some kind of hyperkähler geometry, which typically we Higgs some of the symmetries in the theory. So what are some of the examples? Well, the simple example is M5 branes. So we already said M5 branes, parallel M5 branes give you 2, 0 theory. But if you put them in the presence of an AN singularity, you break half of the symmetry because of the singularity that you're putting it on. So here, I'm depicting here the M5 branes probing in the AN singularity in M-theory context. Notice that AN singularity is 7-dimensional, and M5 brane is 6-dimensional, so it's codimension 1. So this picture is kind of accurate, namely it's codimension 1. The M5 brane can move on the AN singularity in a codimension 1 sense. So you can think about them as domain walls, if you wish, on the AN singularity locus. And the two branches corresponding to the Higgs branch corresponds to moving away from the singularity in this context. And the Coulomb branch, in this case, corresponds to separating the M5 branes on the singularity. And when you separate them like this, then you end up getting a quiver description of the theory, because AN singularity in the M theory gives rise to an SUM plus 1 gauge symmetry, as we know, in the 7-dimensional word volume. And the presence of M5 brane punctuates this to give you finite couplings for each of these gauge groups. So you get for each one of these regions, each one of these strips in this case, you get the corresponding quiver gauge group. So SUN plus 1 in this context, and the bifundamental between them, and the two ends where they are non-compact, they are the flavor symmetries at the two ends. There's also a type 2B realization of this, which I will be using later on. So in the context of type 2B, having a parallel M5 brane corresponding to an AK singularity, so you have a singularity in the geometry is playing the role of M5 brane, and placing them in the presence of a singularity like A-type corresponds in the type 2B language to wrapping these branes, this geometry by D7 branes. So if you have an AN singularity, it corresponds to putting D7 branes, n plus 1 D7 branes wrapped around these corresponding spheres. And the two last spheres are the corresponding non-compact ones corresponding to the two ends over there. So you can see the one-to-one correspondence here between each strip basically gets replaced by a sphere. We can do also something more. One can actually introduce, in the context of these 7 branes, non-trivial geometries or gauge connections on them. And these are the so-called triangular branes or T-branes. And you can introduce triangular branes on the left and the right. And this leads to partially Higgsing some of these gauge groups towards the left corner or the right corner of this diagram. In the middle part, you're still going to have an intact SUN plus 1 gauge symmetry. And these will be equivalent to type 2A constructions of Gaiotto and Tomasiello, which I believe we will hear a little bit about later in Alessandro's talk. Another example is placing M5 branes at the Hojava-Witten wall. So we take M theory with the boundary of the world, and we place M5 branes at the wall. So we take the coincident M5 branes at the wall. This theory will inherit an E8 global symmetry from the fact that there's an E8 gauge symmetry on the wall itself. So this theory will inherit the E8 global symmetry. Now there's again Higgs branch and Coulomb branch. The Higgs branch corresponds to dissolving these M5 branes in the wall. And this corresponds to having finite size instantons for the corresponding E8 gauge group. And the Coulomb branch corresponds to moving them off the wall. Again, in this context, the analog of type 2B, or more precisely F theory realization, is as follows. The parallel M5 branes correspond to AN singularity of type 2B setup that we already discussed. The fact that there's the last M5 brane near the wall gets replaced by the condition that this distance is replaced by a sphere of a different type. So we have a different kind of a sphere towards the end. And the way this works is, in the context of F theory, so we have a 4-dimensional base. So we go from 10 dimensions to 6 dimensions. And you have these spheres which correspond to the AN type singularity. But there's this last sphere in the base which is slightly different from the rest. And what is different about it is that the coupling constant, which is geometrized by elliptic curve in the F theory, is effectively constant away from this other sphere. But as you approach this other sphere, it's fibered non-trivially over it. So you get a geometry of a half K3 over this P1. So this is a sphere with a geometry where the elliptic fibration degenerates at 12 points and gives you a geometry of what's called half K3. If you view the totality of the sphere and the elliptic fiber on top of it, that's a geometry of half K3. And moreover, the way it distinguishes itself in the base is the fact that if you don't even worry about what's going on in the elliptic fiber, in the base you're different by the fact that the normal bundle to these P1s are O-2 for all of these the blue ones. And for this yellow one, the normal bundle is O-1 instead of O-2. In other words, it's a spinor bundle on top of it rather than this cotangent bundle, which is O-2. So sometimes I just denote this fact by just drawing these spheres in the base with these numbers 2, 2, 2, 2, denoting the fact that the normal bundle is O-2, and which is the self-intersection, in other words, of each one of these is -2, but the self-intersection of this last curve is -1, and I denote it by this number 1. So I just denote this by this sequence is 1, 2, 2, 2, 2. The AN case was given by 7 brane. So the AN case that I just discussed, where you had only the 2s, and this would have given just a 2, 0 theory, but I will also denote this same symbol when I'm talking about 1, 0, because I can still dress it up with 7 branes. So sometimes I will not describe this dressing by 7 branes. I'll still talk about this as 2, 2, 2, 2, these curves, and you can add to it the 7 branes and dress it up with it. So then it becomes 1, 0. So I will not, in this picture, I will not label the 7 brane geometry. We have that choice to add at the end. So all the known examples of 2, 0 and 1, 0 conformal theories can be realized in type 2B or F theory realization. The 2, 0 I already mentioned. These are the ADE singularities of type 2B. Now, in the context of the curves that I talked about, I said that we also can get these O-1 curves. But in the O-1 curves are different from the O-2 curves in that if you shrink the corresponding sphere, it leaves no imprint. This is something we are not usually familiar in the context in the physics context. Namely, we usually blow up something if it's singular. But mathematicians blow up the space even if it's not singular. So even if you have a smooth space, they take a point and replace it by a sphere. And that's the more typical situation where they do the blow up, the original blow up. And that's the kind of blow up which leads to what's called O-1 curve. So if you shrink it, there's no imprint in the base. Moreover, if you wanted to go to the maximally Higgs branch, you could first shrink these curves as much as you can and go to the corresponding Higgs branch by, for example, dissolving the branes. In that case, in the context of the E8, the Hoja-Witten wall, you can get rid of these. So one basic strategy is get rid of all these -1 curves, shrink as much as you can, which don't leave any extra singularities, and just keep the ones which lead to singularities in the base. And then, starting from there, you can always blow up and add these O-1 curves by blowing up various points. So the classification will be, roughly speaking, classify the maximally Higgs phase of these 1, 0 theories. And the surprising result that one finds is that all allowed endpoints correspond to orbifold singularities. So all of them, in the context of F theory, give you a base which is 2 complex dimensions mod out by a subgroup of U2 instead of SU2. So we are familiar with modding out C2 by subgroups of SU2, but you can actually mod out by subgroups of U2 without breaking supersymmetry because the elliptic fibration will be non-trivial and compensate for the fact that it's not SU2. Not arbitrary subgroups of U2 are allowed. Some specific ones arise that I will mention. You could even ask about a single curve. What are the possibilities of a single curve? If you have a single curve, the only possibilities are what I listed here, where the self-intersection n goes from -3 to all the way to -12. And these ones will give you extra gauge symmetries. So anything beyond 2, I had talked about 1 and 2 before, but if you do 3, 4, and so on, you get other gauge groups, all the way up to the case where n is 12, where you get the E8 gauge symmetry, and you cannot go any further. So there's a finite list of the ones which have only one P1. And these have been encountered in the context of strong coupling points of heterotic strings. And this is the F theory version of those same statements. One can, in fact, form what's called the non-Higgsable clusters by Morrison and Taylor, that you can actually find the list of clusters where you cannot Higgs any further. And they are finite number. Well, the list is basically here. It's a very simple list. Apart from the known ADE type, which are non-Higgsable clusters, you just have the ones with 1 curve, 2 curves, or 3 curves. The 1 curve where n is going from self-intersection 3 to 12, -3 to -12, and the other ones are these 3, 2, 2, 3, 2, and 3, 2, 2. These are exceptional ones here. And basically what happens is that all the other possibilities can be used, can be combined, use these guys as kind of building blocks connected by the -1 curves. So you get these guys and connected by -1 curves to build up all the possibilities. But not all the possibilities are allowed. And not all the possibilities are allowed because not all of them correspond to having an elliptic threefold, Calabi-Yau threefold, which can be shrunk at a finite point. So the question is, how can we combine these guys to form all the possible allowed building blocks? all the possible allowed base configurations for elliptic threefold. Well, what one finds is that if you shrink down all these -1 curves to nothing, you will get a series of types of endpoints, which are, in addition to the AD that I mentioned, there will be A-type and D-type, similar to the usual AD. So the generalized A-type will look like this. You just have spheres blown up along a line with self-intersections n1 up to nk. And the generalized D-type looks like a D diagram, except the last two numbers are not the usual Dynkin numbers we're familiar with. So the A-type endpoints, so if you have at least 11 of them, so if you have less than 11 of these curves, there's some special cases that you can look at in the paper. But if you have at least 11 P1s, the situation is like this. You basically have all the 2's in the middle, just like what we have for the AN singularities. And then you have some spheres dressed up on the left and on the right, up to 5 spheres on the left and on the right, with self-intersections, which can be any of these numbers or less than that. Namely, any number less than these maximum numbers all the way up to 2. So these numbers could be anywhere from 2 to any of these guys, for the left or for the right. And that's the full classification for the A-type. And these correspond, surprisingly, to U2 subgroups. And the way to read off the correspondence between the U2 subgroups is that if you take the two complex coordinates Z1 and Z2, and you mod out by one of the coordinates by a pth root of unity, and the other one by a q pth root of unity, the q and p can be read off from these ends by this procedure, which is well known by mathematicians. So in this way, we can actually read off from a given geometry endpoint to a given orbifold singularity. So not all orbifolds are allowed, but only these cyclic ones for which the ends I wrote, the allowed ones in the previous page. The D-type endpoints are, in this case, there are no outliers, and you just have the 2's, except the last 2's, instead of being 2 and a 3, instead of being all 2's, it's 2, 3, or 3, 2. Or a 4-2. Again, this D-type is like the usual D-singularity dihedral group, except the cyclic group element is not equal phases in the two elements that we are used to. So these are the endpoints. So when you start with the endpoints, the geometry is still singular. Now you have to blow up. The elliptic fibration, in other words, is not good. And if you want to get a nice elliptic fibration, you have to blow up. That's going to the Coulomb branch or the tensor branch of the theory. In this case, suppose you started, as an example, with the two curves being given by self-intersections -4 and -4. You will end up having to blow up this point in the middle and replacing by a -1 in this way. And then again, it turns out to be singular. And you have to again blow up this point and that point. Blowing up this point gives you this -1 curve, and blowing that point gives you that -1 curve. And in the middle of it, this 1 has turned on to a 3. So you get this geometry, and at the end of it is not singular anymore, and you stop. And what happened here is that if you look at the list we had, this self-intersection -6 gives you gauge group E6, the -3 gives you gauge group SU3, and this one curve is the usual small E8 instanton story where you have an E8 global symmetry for which the E6 times SU3 part of it is gauged. So this -1 curve has E6 and SU3 gauge, and this -1 curve, which has an E8 small instanton theory, has again an SU3 and E6 part of it gauged in this way. So this 4-4 here at the end encodes this structure. The structure, if you blow up into the Couver form, you'll get this. So typically, when you have these endpoints, you have to blow up a bunch of these in such a way that you get these non-Higgsable clusters in the middle, these blue ones. And so each of these yellow ones are these -1 curves, which are like the glue. So you can think about this small E8 instanton, which is the blow-up points, as a kind of a glue between these non-Higgsable clusters. And each one of these has an E8 symmetry. And you have typically some left and the right subgroups, which are gauged. Basically, that's what the effect of this in the Couver language is. So what do we learn from all this? Well, a number of things emerged which is surprising. And one thing we found was that if you look at this list, and if you blow up so that you get rid of the singularity, you don't have a singular Calabi threefold, you find that some repeating patterns emerge. So here I'm just noting some of the repeating patterns here. For example, you get the repeating patterns 4, 1, 4, 1, 4, 1, 4, 1, and so on. And this corresponds to SO8 gauge group on this, nothing, SO8, nothing, and so forth. Notice that SO8 times SO8 fits in SO16, which fits in E8, and that's the E8 part of this one which is being gauged. Similarly here, you have 3, 1, 6, 1, 3, etc. You see here the existence of this E6 gets repeated. Another repeated pattern is 8, 1, 2, 3, 2, 1, 8, etc. Notice that 2, 3, 2 is one of those non-Higgsable clusters. 8 is one of the other ones, and then they are glued by these ones. And then you get E7, and then some nothing, and then SU2, SO7, SU2, nothing, E7, and so forth. So quite interesting pattern. And so the question is, what is the meaning of this? Well, it turns out that if you try to keep these gauge groups intact, like SO8s, and blow down these ones, what you end up getting is this picture. So you get 2, 2, 2, 2, which is the usual AN singularity we're familiar with, except the fiber is just SO8. So this is beginning to look like the one we started before in some ways, where we had D7 branes wrapped around them. This is the D7 branes corresponding to SO8s. And the similar here, you get E6. 7 branes corresponding to the E6 type, and these correspond to the E7 type. So in other words, what happened here is that if you got rid of these ones, you end up with this picture, which is there's something hidden here, in other words, which is this small E8 instantons are hidden here. And then there's an MTA interpretation of this. And the MTA interpretation is also very simple. You take M5 branes probing the D or E singularities. For example, say you have two M5 branes. And then you put them, and then suppose you have a locus of E7 singularities. And remember, this is 7-dimensional, and this is 6-dimensional locus. So it's 1 dimension higher than this M5 brane. Suppose you bring two M5 branes from outside and place them on the locus where there's an E7 singularity. And then suppose you separate them. When you separate them, you should get E7 gauge symmetry punctuated by these M5 branes. So you get E7 times E7 times E7 the same way we were talking about. Except there's something strange, because this suggests bifundamental E7 matter, which we're not familiar with. So the M5 brane probing E7 singularity should have some kind of matter, which is unfamiliar. But now, actually, we are finding the answer to it. This is precisely where those other spheres in the middle were hidden. And so, in fact, they give you fractional M5 branes. So the M5 branes, if you place them on the E7 singularity, they could split. And the geometry that you get is precisely this middle structure that you have. For each one of these blue lines, you get these corresponding spheres in the F-theory language with this corresponding gauge theory pattern. So in other words, you can think about this conformal theory, which is if you shrink a 1, 2, 3, 2, and 1, as the would-be bifundamental E7 matter. So this is the bifundamental E7 matter, is this non-trivial superconformal theory 1, 0, which has E7 times E7 global symmetry, which can be gauged if you wish. And similarly for the D and the E. In other words, so a single M5 brane in the presence of the A singularity gives you the usual bifundamental we are familiar with. But if you have a D and an E singularity, the bifundamental does not exist for the D and the E, but it is replaced by a non-trivial superconformal field theory with 1, 0, which is playing the role of a bifundamental matter. So that's what this is. And so we can do this for all the D and the E, but I don't bother showing all of them. But anyhow, for each group, you get such a pattern. There's also the M-theory realization of these in the large and dual context. So for example, if you just take NM5 branes, you get ADS7 times S4, and you can mod out by some ADE singularity. That's the same thing as placing M5 branes in the presence of an ADE singularity. In the geometry, you have this S4 where you have two orbifold points corresponding to the north and the south pole of the sphere. in this context, this would correspond to an E7, for example. As an example, if you do the E7 version of this I was talking about, in the language of the chains I was telling you about, this corresponds to the chain 5, 2, 2, 2, 2, all the way to 5, where the first of the last curve, 5 and 5, become non-compact. So if you take the last and the first curve to be non-compact, then you get this large N dual. Of course, we can still keep it compact, and it won't have a large N dual in that context, but making these two 5s non-compact leads up to this as this dual. Similarly, if you take M5 brane and bring it to the Hojava-Witten wall, it's the same thing as modding at ADS7 times S4 modded by Z2. So the large N dual will be this S4, where there's a boundary S3. And this will be dual to this geometry of this 1, 2, 2 I was telling you about. And you can combine them together as well with ADE and Z2. So some of these have its large N dual. And interestingly enough, this collection of the two somehow corresponds to elongating the sphere, so to speak. And the two endpoints correspond to these singular points, which are where you get the gauge symmetry in the bulk, which is the global symmetry of the corresponding conformal theory. So there are these other ones which have other numbers. In general, we had these other things at the end going on, up to 5 spheres. So those will be something which will not have a nice gravity dual. At least whatever is going on will be some kind of little thing going on near the singularity, so it's hard to see using the bulk gravity. Okay, so this is as far as I was going to tell you about the classification of these theories. Of course, just to end the discussion about the classification, on top of the classification I told you, you have to allow then to blow up points by putting -1s. It turns out those are typically finite in number. You cannot blow up infinitely many times, except for the 1, 2, 2, 2 case. And also, you're allowed to put these 7 branes, like the type I told you about before, and in addition, put the analog of the T brane, which breaks still Higgs the sum of the branes. So to have a complete classification, you will also have to introduce what are the possibilities of putting 7 branes on top of these spheres, and what kind of triangular branes you can turn on them. So now I want to move on to some computations in these theories, and in particular, the computations of the superconformal index that I mentioned briefly. I guess I mentioned this in my last strings talk last year, and this was done in 2 collaborations. And basically, the idea is that if you try to compute the superconformal index for these 6-dimensional theories, you get a partition function, a product of 3 factors, which correspond to partition functions of certain theories on R4 times T2. And you basically can think about these as compactifying these theories on a twisted product of R4 times T2, where the fibration is non-trivial. And these ended up giving a structure of the form e to the minus nt times z of n T2, where the interpretation is as follows. If you think about these 6-dimensional theories and compactify it on a T2 times R4, you can think about, since these theories have tensionless strings, you can think about the strings wrapping the T2 n times. So there will be instantons contributing to this, which are the string instantons. So the basic statement is that the computation of the partition function of the 6-dimensional conformal theories on R4 times T2 gets reduced to the computation of the instantons, where you have n strings wrapped around the T2, and this is weighing the tension of the corresponding string. You sum over the number of strings, and this gives you the piece that goes here and computes for you the superconformal index. So in other words, from a worksheet computation, the strings that these theories have, you can deduce the partition function of the target theory, which is, in this case, the theory of superconformal index for the 60 theory. So this is an example of what we would like to do as we do in string theory. We have a worksheet computation to compute some quantity for the target theory. This is already happening in this context for this 6-dimensional superconformal field theory for a supersymmetric protected quantity, in this case, a superconformal index. So, and this z of nt2 can be viewed as the refined topological string partition function or the Nekrasov partition function, depending on one's viewpoint, for this R4 times T2. Now, for the theory of M5 branes, probing AN-1 singularity, you get these covert theory I mentioned before, and you have M-1 of these spheres, let's say, and so therefore you get M-1 different strings. In this case, in the case of, for example, type 2b, they correspond to D branes wrapping around this, giving you tensionless strings. It turns out the corresponding strings here form a 4, 0 supersymmetric theory in 2 dimensions. And if we denote the number of strings, the wrapping number k1, k2 up to km-1 by these numbers, the corresponding 4, 0 supersymmetric theory is given by some kind of a covert theory of an unfamiliar type, perhaps. I won't bother mentioning all these labels, but anyhow, you have some kind of a matter structure, the 4, 0 matter structure. Here we have written in the language of 2, 0 matter, that you can describe these theories. So in other words, the basic point I'm trying to make here is that we do know what is the string living on the wordsheet of these, what is the wordsheet theory of these strings. And this is basically this covert theory, the 4, 0 covert theory given by this. And you can compute the elliptic genus of these theories using techniques that have been championed recently by these groups. And you recover the answer for topological string partition function or Nekrasov partition function using this as well. So in other words, you can now view the computation for the 6D superconformal field theory in terms of a wordsheet computation with this covert theory. That doesn't sound too good. That's better. Now, what does one learn from such computations? Well, one learns, as I mentioned in the last strings conference, is that unlike fundamental strings, tensionless strings do form bound states. So for fundamental strings, we're familiar with the fact that if you have 2 strings, their partition function is simple to compute by an Oberford-like formula. For example, 2 strings give you 1 string squared, or this kind of a computation as we're familiar with. But this is not true for these kind of strings. The strings that we now have in the context of strings of these 60 conformal theories do not satisfy this relation. The partition function of 2 of them are not this, and this signifies the fact that they form bound state. In other words, these strings are sticky. Now, there's a dual description which involves quantum mechanics. And the way that works is that if you think about in the M-theory language, the M2 brane suspended between M5 brane gives you these tensionless strings. And the word volume of M2 brane is 3. That's 2 plus 1. So either you can take the 1 to be small or the 2 to be small. If the 1 to be small, you get the wordsheet description that I was talking about, the tensionless strings. But if you take the 2 to be small, in this case, this T2 that I'm talking about, you get a one-dimensional theory or quantum mechanics. And so, so then, in the one-dimensional sense, you can think about these M5 branes as giving some kind of a operator acting on this quantum mechanical setup. It turns out that, as I mentioned before, in last year, the Hilbert space is characterized by Young diagrams, and you get some operator corresponding to these M5 branes, which go from one Young diagram to the other, and you can do the computation of these by just doing a quantum mechanics computation for any number of them. So this gives you a partition function of M5 branes, parallel M5 branes, in this way. But now, what about E string? And so this is the new story. So E strings corresponds to M5 brane, bringing it near the boundary of the wall, boundary of the universe. So if you have an M9 brane or M9 wall, and you have M5 brane next to it, and there's an exceptional string. So the boundary here, the time stops here at the end, and therefore you have some state which we associate with the M9 brane. And then you have the propagation in time, and then you have some defect operator which corresponds to this M5 brane. And so if you're interested in the contribution of the 2 E strings, for example, which is the first non-trivial case, you get a contribution of the sum over of this type, where you get a contribution of these wave functions of the M9 brane and the domain walls contributions in this form. Now, using recent results for topological strings on K3 over 2, I remind you that this E string corresponded in the F-theory language to half K3. So the partition function of that can be used to compute the partition function of E strings. And this was done recently by this group. You can extract from that data the partition function Z2. And therefore, you can get this M9 boundary state up to 2 E strings. But now you can do something for fun. You can now go back to the original Hojava-Witten setup where you have two boundaries in the universe. You have two M9 branes. And then you have placed a single M5 brane in the middle. And then the partition function will be, you have a boundary state M9. You propagate. You have a domain wall defect or M5 brane defect. And then you can propagate, and then you go to the other boundary. But you see, you can remove this M5 brane. And if you remove this M5 brane, you end up getting heterotic string. So you can recombine these E strings, these exceptional string for this theory, which has exceptional group has symmetry, and you get the heterotic string. So therefore, this computation should give us the partition function of heterotic string. This is a bit strange because even though we know it has to work in some ways, it's strange because I already told you that the partition function, these E strings are sticky and form bound states. So the partition function of two of them does not have the property that we expect for fundamental strings. But somehow out of that same ingredient, we better be able to get up the non-sticky heterotic string out. And so indeed it does in a very non-trivial way. I have not bothered to introduce every term in these expressions. I just want to flash it so you see it's not completely trivial. You get some, you compute the partition function of these two heterotic strings in terms of these are the fugacities having to do with the E8 Wilson lines for the left and the right side. And these epsilons have to do some rotation symmetries of this vibration data. And so you end up getting this complicated computation where these ends are some complicated extensions of theta functions of the E8 lattices and the denominators of these theta type. This does not look familiar compared to what we expect the answer to be. Namely, the Z1 of heterotic string is the usual theta function contributions and the oscillator contribution for the 8 dimensions. And if you just take two heterotic string, you have this simple formula for it, the one I just told you. And it turns out that this formula is equivalent to this, at least up to the order we have checked. We have expanded to a large order, and they agree. So this is a very non-trivial identity among these functions. So I see that my time has run out from Lars, so I'll conclude. So classification of maximally Higgs branches of 1, 0 theories is completed within F theory, leading to a generalized ADE classification. That was the first part of the talk. And secondly, the strings in the Coulomb branch of some of these theories are being better understood. And it'd be good if we can understand more of these and how we describe the worldsheet theories in more detail. And to use these, in the talk I showed you how we can use this to compute supersymmetry protected quantities, at least one such thing, superconformal index. It would be interesting to see if we can start that and as a springboard to computing even non-supersymmetric quantities in some kind of a perturbative expansion. So I'll stop here. Thank you.
Well, thank you. We have time for a few questions. Ed.
So in M theory, there are several different kinds of D and E singularities where the exotic ones have reduced gauge symmetry. I wonder if that plays a role here.
We were just talking about the regular ones, so we haven't studied all the possible ones, but that would be interesting to study.
More? Okay. If not, let's thank the speaker again. Okay.